Okay, good morning, all of you. Let's get started. Uh, Let me show you the solutions for quiz, whatever we attempted on Saturday. So this is the question paper. These are the questions. This is very simple quiz, understand? And you need to use consistent units, and you need to adopt uh, the conventions that we discussed in the class. So let me show you the solutions. Simple, this first problem, you can use single element. This is the stiffness matrix, and depending on the boundary conditions, you can actually get the reduced equation system. Slope is 0, deflection is 0 at fixed end. Applying that boundary condition, it reduces to 2 by 2 equation system. Once you get the unknowns, that is deflection and rotation at the free end, you can determine the deflection at any point along the length of the beam using finite element shape functions. And here there is a distributed load, so you need to apply fixed end correction. Okay, so this is the solution for question 1. On similar lines, question 2 also. Okay, except that here a beam element and a spring element is given, and we solve these kind of problems. Okay, the boundary conditions at the fixed end of the cantilever for the second problem. Fixed end of the cantilever, slope is 0, deflection is 0, and also here this you can see the boundary condition here. Deflection is allowed, but slope is 0, theta is 0, and V3 is nothing but this deflection at node 3, which is a spring element. It is also 0. Based on that, you can actually eliminate the rows and columns corresponding to the degrees of freedom, which are 0. And finally, you get one equation, one unknown. You can solve for it, for the unknown, and use finite element interpolation. And then you can determine the deflection and the rest of the quantities. Stress resultants like bending moment, shear force. Here it is asked to determine the deflection and bending moment. So that is what is solved for. Okay, even though I am showing you expressions alone here, it is expected that you also show it as in the form of a figure. Just intuitively draw how this profile looks like for deflection in the first problem, deflection and bending moment in the second problem. And the third problem is straightforward, or straightforward in the sense you need to apply your concepts that you learned. Okay, it's not really falling under the category of general one-dimensional boundary value problem, but once you solve a number of problems, you can easily guess when there is second derivative term is there, what are the quantities that are going to appear, and when there is a first derivative term is there, what are the quantities that are going to be appearing. Whenever you have second derivative terms, you will see something like B transpose, B transpose, or B transpose B, such kind of term. And whenever derivative term is there, you are going to see B or B transpose. Anyway, you can start from the first principles and derive the element equations. And this is how the element equations looks like for the third problem. The element equations for third problem looks like this, and it is here it is asked three linear elements you need to adopt. Okay, 3 linear elements you need to adopt, and these are the boundary conditions. 3 linear elements is going to result in 4 nodes. 3 linear element is going to result in 4 nodes, and 2 of the boundary conditions are given, which are 0. At the extreme points, it is 0. So you can solve finally reduced equation system. You end up in getting 2 by 2 equation system, and that you can solve it. That you can solve to determine the unknowns. Here, C is equal to 0 is the starting point. C is equal to 3L is the ending point. So C is equal to L, or sorry, X is equal to 0 is starting point. X is equal to 3L is the ending point. So X is equal to L and X is equal to 2L are the points. So C evaluated at X is equal to L, C evaluated at X is equal to 2L, that is what is solved. In terms of here numerical value of M is not given, so in terms of M, okay? So you need to start from first principles and get the element equations and apply the boundary conditions and solve the reduced equation system. And the fourth question is, here a 4 node element is given and the nodal locations are also shown here. So based on that, you need to derive using Lagrange interpolation formula, you need to derive the element shape functions N1 to N4, okay? And then use isoparametric mapping. This is the actual element. The first figure shows the actual element. And this element is going to be mapped onto this parent element. This parent element, 4 nodes, locations of 4 nodes is also shown. Okay, so you can easily, based on whatever the concepts that you learn for 3 node element, based on the same concepts, you can extend that idea and write the isoparametric mapping relation. X is equal to sum of all, or X as a function of S is equal to this one, sigma Ni Xi. Ni I goes from summation goes over all the nodes. So there are 4 nodes here. So X is equal to N1 X1 plus N2 X2 plus N3 X3 plus N4 X4. And N1, N2, N3 expressions you need to write in terms of S coordinate system. In terms of S coordinate, in the parent element coordinate system, you need to write the element shape functions, and then that you can easily do it using Lagrange interpolation formula. So X is equal to N1 X1 plus N2 X2 plus N3 X3 plus N4 X4. Based on that, you are going to get a relation, or if you simplify, you are going to get X as a function of S, and Jacobian is nothing but derivative of that, derivative of X with respect to S, okay? And that is this one. And once you get derivative, here it is asked to determine the shape functions N1 to N4. That is what we have written. And the strain displacement matrix. Strain displacement matrix is nothing but the relation that is connecting strain with the displacement. That you can obtain once you try to calculate derivative of u with respect to x, which can be written using chain rule. This d here du ds derivative of u with respect to s, which can be obtained from this relation and multiply with the derivative of s with respect to x. That is Jacobian, inverse of Jacobian. So this is what is B transpose D, and now you can easily identify what is strain displacement matrix. So this is this B transpose is nothing but I'm unable to highlight here. This quantity is B transpose, including that 2 by L. Okay, that is B transpose. So this is what is expected in 4th question. The idea of testing you in this is you can easily derive the shape functions as well as these kind of relation for even any of the custom, depending on your requirement or for research purpose. if you want to use higher order element. So you can make use of these kind of relations. So that is the idea of testing this one. And also please note that in all commercial software, you may have only up to quadratic elements. Okay, for one-dimensional case, most of the times it is going to be limited only to 3-node element. For research purpose, or once you understand the concept, you can easily derive the shape functions for any higher order element. That is the idea of testing this question 4. And question 5 is straightforward. It is a 3-node triangular element. The nodal values are given. So depending on the coordinates, you need to identify the nodal coordinates. Based on the nodal coordinates, 3 nodes are there. And also I explained to you how to derive shape functions for this kind of 3-node triangular element. So shape functions and derivative of shape functions. Shape functions are going to be linear. Derivative of shape functions with respect to either x or y is going to be constant. Okay. So once you have this, you can easily compute the u value, derivative of u with respect to x, derivative of u with respect to y. Okay. At this point, and this is the value of the location of the point of interest is that one. So at that point, you determine what is u and derivative of u with respect to x, derivative of u with respect to y. Okay, so this is the solution for all the 5 problems, and I hope you have done properly. Okay. Anyway, whatever best we can do under this pandemic situation we are doing, you need to put effort to improve your understanding. Okay, and now let's proceed further. This is the 8-node element that we discussed. 8-node quadratic. It's a quadratic element because if you see the shape functions, the shape function expressions, highest order, the power of the order with respect to s or with respect to t, it's going to be highest order is going to be quadratic or second order. So that's why it's 8-node quadratic and serendipity element. Serendipity in the sense it's not falling under, or you will not be able to directly use the Lagrange interpolation formula. So that's why the serendipity word is appended to this one. Okay, element. It's not a Lagrange element, 8-node serendipity element. So once you understood the procedure that we discussed in the last class for this 8-node element, even if one of the, like, here the 8 nodes are numbered like this: 1, 2, 3, 4, 5, 6, 7, and 8. And so let's say 7-node element. I want you to write the shape function or derive the shape function expressions for 7-node element. You can take, except this 8-node, you can take the rest of the 7 nodes. Okay, and such kind of element, how do you derive the shape functions? Apply the same concepts, whatever you learned here. Okay, whenever you want to write the shape function expression for a particular node, you need to keep in mind that the value of the shape function for that node evaluated at that node should be equal to 1, and it should the shape function value of that node evaluated at other nodes it should be equal to 0. So that is first thing. And also the shape function, the value of shape function of a particular node is going to be equal to 0 on the edges along which it's not part of those edges. Along the edges for which it's not part of those edges, the shape function value of that particular node should be equal to 0. So these points you need to keep in mind. And also I emphasize to you, you cannot simply remove one of the element. Let's say this is an 8-node element. For this 8-node element, we derived the element shape function expressions here, and then if I ask you to write shape function expressions for a 7-node element, you cannot just simply remove one of the node, and then you can use the same relations or same expressions, because it's going to violate the condition that sum of all shape functions evaluated at any point on the element is equal to 1. It violates that condition. Why it's going to violate that condition? So let's see that here 8 node element is there, and 8 node element is going to satisfy the condition. Here whatever expressions we derive, it's going to satisfy the two first conditions that I mentioned. First thing is the shape function, the value of this n1 to n8 are going to be equal to 1 when they are evaluated at that particular node, and they are going to be equal to 0 when evaluated at other node. So with that, so now let's say you are removing this 8th node. When you remove this 8th node, and if you try to adopt same expressions, what's going to happen? At this 8th node location, for a 7 node element, at this 8th node location, all the shape functions, n1 to n7, sum of all shape function values n1 to n7, evaluated at this 8th node is going to be 0. And so it's going to violate the condition that sum of all shape functions evaluated at any point on the element should be equal to 1. If you just simply remove this 8th node and take the other expressions for these, whatever we derived, and adopt those for 7 node elements. So you need to keep that in mind. Okay. So if you want to derive element shape functions for 7 node element, what you can do is you adopt the same philosophy or same idea here, whatever we adopted. So shape function, let's write the shape function expressions for expression for node 1. So node 1 expression should be equal to 0 along this edge, along this edge. So the equation of this edge is S is equal to 1. Equation of this edge is T is equal to 1. So this shape function expression should consist of S minus 1, T minus 1 term. So when you include that, you are eliminating all these nodes along these edges, And we are trying to derive for 7 node elements. So 8th node is not there. Node 2 is there. How to remove or how to eliminate this node, or how to make n1 is equal to 0 at node 2. So one way you can do it is, since 8th node is not there, this node is not there, what is the point, what is the condition that is being satisfied by this location? Node, wherever node 2 is there, what is the condition that is being satisfied there? It's S is equal to 0. S is equal to 0 is the condition that is satisfied at that location. Okay, and also T is equal to minus 1. But if I use T is equal to minus 1, then it's going to be 0 here also. It's going to be 0 if I include T is equal to minus 1 term, it's going to be 0 along at this location also. So what I can do is I can include the term S is equal to 0. So the shape function expression for 7 node element consists of S minus 1 term, T minus 1 term, and S. Okay. So you need to start something like N1 is equal to A0 times S minus 1, T minus 1 times S, and determine that A0. You can actually try doing it, okay, and then you can use your imagination and all your creativity to derive these expressions. And if you do that, you can write the shape functions for all noded elements, like 4 node element, 5 node elements, 6 node, 7 node, 8 node, and 9 node element. So here 4 node element is Lagrange element, 6 node element is Lagrange element, 9 node element is Lagrange element. What about 5 node, 6 node, and 7 node elements? 5 node, 6 node, 7 node, and 8 node element. They are serendipity elements. So here the general expressions are given for this kind of node numbering. Okay, and this is the node numbering that is adopted. And if you say four node element, the nodes are located at 1, 2, 3, 4. And 5 node element, the nodes are located at 1, 2, 3, 4. And 5th node is located at midpoint of one of the edges. Similarly, 6 node element, if you want 1, 2, 3, 4, 5, 6, or you can take this. So like that, okay. These are the expressions that are given here. You can cross check these expressions. And what is the benefit of these kind of elements? What is the use of this 5 node, 6 node, or 5 node? 5 node, 6 node, 7 node. These kind of elements. What is the use of these elements? I told you these these elements can be used as transition elements. Okay. I think I made a mistake, or I mentioned in my previous statement that 5, 6 are Lagrange serendipity elements. 5, 7, and 8 are serendipity elements. 4, 6, 9 are Lagrange elements. So whatever I just mentioned, elements, you can read this, elements with number of nodes between 4 and 8 are known as transition elements. You can also use 4 depending on the situation. Anyway, here some typical examples are shown. We'll see that. Okay. So some of these elements can be used as transition elements. They are useful when a transition from quadratic elements to linear elements is desired. And a figure shows proper transition from a mesh with 8 node elements to one with 4 node elements through use of 5 node transition elements. So here you have I told you it's not necessary over the entire problem domain you need to adopt same type of elements. You can adopt lower order elements, or the elements with less number of nodes over a particular region, and more number of nodes at a particular elements with more number of nodes at a particular region. But in between, you should have smooth transition. Okay. So here 4 node elements are used, and here 8 node elements are used. So how to connect 4 node elements to 8 node elements? You can make use of 5 node elements. So 5 node transition element, and 4 node bilinear element, 8 node biquadratic element. 8 node element is biquadratic element. 4 node element is bilinear element. And 5 node element is a transition element. Over one of the edge, it's going to have quadratic variation. Here, along this edge, it's going to have quadratic variation. Along this edge, it's going to have linear variation. Okay. Similarly, another here it's an invalid transition. An example of invalid transition is shown. So let's see that. Here 4 nodes are there. Okay, and here 8 node elements are there. Here it is nicely shown 5 node elements are used, but instead of that, if you plan to use 4 nodes here and 8 nodes suddenly here, then interpolation is going to be a problem. Okay, so along this edge, you will be having some problem. So you cannot directly use bilinear elements adjacent to that biquadratic element. You should have transition element. So invalid transition from linear to quadratic solution. So that one here it is shown here. Okay, so that is all mentioned here. You can go through that. Okay, so now any questions here? So with this, we noted the shape function expressions for all elements, 4 node to 9 node elements, for a 2-dimensional, for solving 2-dimensional problems. Okay, any questions here? So what I suggest is you go through these expressions which are given more general way, and then convince yourself, and then whether you will be able to derive at least shape functions for 5 node, 7 node, and whatever shape functions you derived, just compare with these expressions that are given, and then try to correct yourself. Okay. So now here an example is there. Derive explicit shape function expression for 5 node rectangular element shown in figure. Which finite element? This is the finite element for which you need to derive the shape functions. Okay. So whatever logic that I explained, you can make use of that. So if you want to derive for n1, include x is equal to 2, term should be there, y is equal to 1. So x minus 2, y minus 1 should be there, and x is equal to 0. So n1 should consist of x minus 1, y minus 1, and x term. So let's see here. Okay, anyway, you please see that. Okay, and you can determine the coefficient. And if you want to derive the shape function for n5, it's straightforward. Include this line, include this line, include this line. X is equal to 2, y is equal to 1, x is equal to minus 2. So it should consist of x minus 1, x plus 1, and y minus 1. Okay. And what about shape function expression for n3? Node 3. Node 3, include this line and include this one. That's it. X is equal to 2, y is equal to minus 2, y is equal to minus 1, and x is equal to minus 2. So y plus 1, x plus 2 should be there for n3. So let's see that n3. Anyway, here it is given. It's given in the fractional form. You can check. Okay. So once you write the expressions either in S coordinate system or X coordinate system, here why the expressions are written in terms of S coordinate system, because here directly these formulas are used. These formulas are based on S and T. S is defined as like this: 2x divided by a. S is defined as 2x divided by a, T is defined as 2y divided by b. A and b are nothing but here. A is this dimension, b is this dimension. So same thing here, applying, you want to apply those equations, you need to find what is A. A is nothing but 4 units, B is nothing but 2 units. So with that, find the relation between S and X, T and Y, and then use those expressions and then convert in terms of X and Y. You can do either this way. Okay. So you can compare the expressions that are given here with the way that I explained to you. You please write it, and then you see whether they both are same or not. It should be same. So once you got these expressions for n1 to n5, you can plot them. You can plot and see whether these whatever expressions that you got, they are making sense or not. So for example, n5 is plotted. Shape function expression for node 5 is plotted. We can see from this figure, this shape function expression for fifth node or node 5, n5 should be quadratic along this edge, and it should be equal to 0 along this edge, it should be equal to 0 along this edge, it should be equal to 0 along this edge. So that is what is shown here. It is quadratic. Please note that it is plotted in Mathematica. This plot is from Mathematica, and you to check closely whether this is actually coinciding with 0 or not, you can see here it is plotted from -2 to 1. Okay, and here you need to zoom it. Then you will see whether this point coincides with 0 or not, and this point coincides with 1 or not. Similarly, n3 is plotted. N3 is going to be linear along this edge. It's going to be linear along this edge. It's going to be 0 along this edge, 0 along this edge. So that is what is plotted. Okay, any questions here? Any questions? If there are no questions, then we are ready for isoparametric mapping for two-dimensional elements. Okay. Isoparametric mapping similar to what we did for one-dimensional element. For two-dimensional element, I already showed you this whatever expressions that we derived here, shape function expressions, they are all for parent element, s going from -1 to 1, t going from -1 to 1. So irrespective of whatever element you have, here, you are going to map onto a parent element with s coordinate going from -1 to 1, t coordinate going from -1 to 1. So please take a note of these two figures. This is for a 4-node element and 8-node element. 8-node element is a quadratic element. To emphasize that, here the edges of the element are, the edges of the actual element are drawn for a more general case of having curved edges. This 8-node element that is shown here, why it is shown like this, whereas why it is shown straight edges here? Because 8-node element is a quadratic element. So even geometry, you can have quadratic, it can capture this variation of geometry which is quadratic. So curved edges. So the edges are shown to be curved. But irrespective of whatever element you have, it's going to be mapped onto a parent element, where s goes from -1 to 1, t goes from -1 to 1. Parent element is going to be a rectangular element, okay, irrespective of whatever element you have. So please take a note of it. Any questions here? I don't know whether you are following or not, or is my explanation so clear that there are no questions? Either way it should be. Anyway, if you have any question, please don't hesitate. And one important announcement I want to make, please note that I announced the dates for quiz 1, quiz 2 and final exam well before the beginning of the semester. At the beginning of the semester, I mentioned those dates, okay? But in spite of that, actually there was a small overlook that I made. Initially I mentioned 23rd, but later somebody corrected. It's a 24th Saturday, so that's what happened. Quiz 2, okay? Except that I already announced all the dates, and with current situation, COVID situation, okay? And you can see here a lot of uncertainty. We don't know what is going to happen in the next 1 hour. With this kind of uncertainty, let's have the exam on May 15th. Okay, May 15th is what the date that is announced. Let's have the exam on that day. Okay, and then please, what happened last year is I did not teach this course. Some other instructor taught this course last year. Same MTech batch last year, and then this exam was not conducted, and there was a lot of delay in giving the grades for this course. Okay, almost 9 months delay was there. So I think grades were announced somewhere in February or January of this year, 2021. Okay, so I don't want that kind of thing. I want to close this course with, in all respects, as early as possible. So let's stick with May 15th final exam date, and then whatever we will be able to cover, we'll be covering. This is just an additional note, okay? So there is no change in the plan. That's what I want to inform you. And so hope you have taken note of these two elements, actual element as well as parent element. And you can see here, you can see how the nodes are numbered. Nodes are numbered 1, 2, 3, 4 in the counterclockwise direction. Here also nodes are numbered in the counterclockwise direction. And here, you can see here, the nodes are numbered here also in the counterclockwise direction. but the you can see there's 1, 2, 3, 4, 5, 6, 7, 8. Okay, the nodes are numbered in the counterclockwise direction. And the important thing that you need to keep in mind is, in some of the textbooks or some of the authors, they are going to number the here, especially for this 8-node element. They are going to number the corner nodes first. Okay, somebody may number it as 1. This node has, instead of this node has 1, and this has 2, 3, 4, and afterwards number the nodes, the mid-side nodes, 5, 6, 7, 8. I hope it's clear. So the node numbering, some others or some textbooks, you may see something like 1, 2, 3, 4, and then 5, 6, 7, 8. Similarly, here it's in some textbook you'll say 1, 2, 3, 4, 5, 6, 7, 8. So you need to keep a watch on that, how the nodes are numbered. Okay, you cannot mix up the things. Then the expressions are going to be different. That's what I want to convey to you. So now we noted that irrespective of whatever element we have, we are going to map onto a regular element. But the node numbering should be consistently either clockwise or anti-clockwise for both the actual element and parent element. That you keep in mind. So now with this, let's see what is isoparametric mapping for two-dimensional case. Whatever one-dimensional case we noted, we have one more dimension, so we need to write the expression for that as well. And also please note that here in the just now I explained to you example 4 or question 4 in quiz. Sorry, question 4 in quiz. So what is this? This is nothing but isoparametric mapping. X is equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. X as a function of s is equal to n1 as a function of s multiplied by x1, n2 as a function of s multiplied by x2, n3 as a function of s multiplied by x3, n4 as a function of s multiplied by x4. So that is what this is. So now same thing for two-dimensional case, n1, sorry, x instead of as a function of s alone, it's going to be a function of t. S as a function of s and t is equal to sigma ni xi. Ni is now going to be a function of s and t. Similarly, y as a function of s and t is equal to sigma ni yi. Ni is going to be a function of s and t. So please take a note of this. Here, where xi, yi are the nodal coordinates of actual element, s and t are the coordinates of nodes for the parent element. So please take a note of these two equations. And for completeness, let's read this. The basic concept of isoparametric element was introduced earlier in the context of one-dimensional problems. Essentially, the same idea applies to two and three-dimensional problems. Just you extend that idea, okay? The parent element for two-dimensional problem is a 2 by 2 square defined in terms of s and t with origin at the center. So that is what I told you to make a note. S goes from -1 to 1, t goes from -1 to 1. Irrespective of whatever element you have, you are going to map onto a parent element with s going from -1 to 1, t going from -1 to 1. So that is basically what is 2 by 2 square is nothing but that one. The nodes are placed symmetrically on the parent element. That also I emphasized. So whatever figure that you already looked at, that shows parent element for 4-node quadrilateral, 8-node quadrilateral with curved sides. Okay. So this is isoparametric mapping. What is isoparametric mapping? Same set of shape functions we are going to use even for interpolating the geometry. So that is what is isoparametric mapping. So once you got this, S as a function of S and T, Y as a function of S and T, you need to go back to your 12th class mathematics. Okay? You need to go back to your 12th class mathematics, then you can write all these expressions. And n shape function for ith node, ni is function of S and T. So when I want to take derivative of shape function with respect to S, I need to use chain rule. Partial derivative of ni with respect to S is x is function of S and T, y is function of S and T. And what about S and T? S and T are, again, if you find the inverse relation, S and T are also functions of x and y. So here we are taking partial derivative with respect to S. So the chain rule goes like this: ni partial derivative of shape function with respect to x, partial derivative of x with respect to S, partial derivative of shape function with respect to y, partial derivative of y with respect to S. So please take a note of these two equations. These are all based on the concepts which you must have learned as a part of your 12th class mathematics, or at least engineering mathematics. Okay, in your first year undergraduate course or second year. I don't know exactly what is the curriculum now, but as a part of engineering mathematics, these kind of relations or these kind of concepts you must have learned. So I hope you have taken note of these two equations and these two. And now, if you have taken note of these two equations, you can put these two equations. You can put these two equations in a matrix and a vector form. You take this one, writing two equations in matrix form. These two equations in matrix form, it's going to result in that. And here you can see Jacobian. J is used and J is bolded here. J is bolded. 1 second. In a quiz, this J is not bolded. Or here actually J is not bolded. Okay. But for one-dimensional case, J is a scalar quantity. For two-dimensional case, J is going to be a matrix. For two-dimensional problems, J is going to be a matrix. So that matrix is this one. So now here, what this relation is giving, derivative of shape function with respect to parent coordinate system S and T, derivative of shape function with respect to the parent coordinates, how they are related to derivative of shape function with respect to the actual coordinates, actual element coordinates, or derivative of shape function with respect to S and T, how they are related to derivative of shape functions with respect to x and y. So that is how you need to look at it. The derivatives of shape functions with respect to S and T, how they are related to derivative of shape function with respect to x and y. They are related through this Jacobian J. They are related through this Jacobian J. If you give me time, then I will once again show you similarity between whatever we just discussed. Quiz problem. This derivative J is defined as derivative of x with respect to S. Okay. So J is connecting derivative of X with respect to J is connecting derivative of X to derivative of S. Same thing here. J is connecting derivative of shape function with respect to S and T to X and Y. So you please take a note of it. If I want inverse relation, suppose here this relation gives, if I know the shape function derivatives with respect to X and Y, I can find derivative of shape function with respect to S and T. But usually it's the other way, it's the opposite. Usually we know, you can see all the expressions for shape functions we know with respect to S and T. So I can easily calculate derivative of shape functions with respect to S and T. So I want the inverse relation. If I want inverse relation, I need to take inverse of J. It's a 2 by 2 matrix. Let's say 2 by 2 matrix A, B, C, D. Inverse of A, B, C, D matrix. How do we get it? 1 over AD minus BC. Okay? 1 over AD minus BC. And then you need to this A, B, C, D. Some of the terms you need to append negative sign, some of the terms you need to interchange. So that is how you get it. You go back to inversion of 2 by 2 matrix, the formula. Go and see that, how it looks like. So based on that, we can actually find the inverse of J. Okay? So if you do that, this is what you get. 1 over AD minus BC. That AD minus BC is written as determinant of Jacobian. Actually, 1 over AD minus BC is nothing but determinant of that matrix, ABCD. So please take a note of this. And the important thing is this determinant should not be 0. Determinant of Jacobian should not be 0 for this mapping or for this relation to be valid. If it is 0, then it goes to, this quantity goes to infinity. Then we will not have, we will have singularity. We will end up in getting singular case. First of all, what is the use of this derivative of shape functions with respect to X and Y? If you want to find the strain value, you need to know the derivative of shape functions with respect to X and Y. So if derivative of shape function with respect to X and Y, it is infinity, that means strain goes to infinity. If strain goes to infinity, stress goes to infinity. So it's going to become singular. So to avoid such situation, determinant of J should not be equal to 0. So that is the condition that we are going to apply. That is the condition that we are going to apply for valid mapping for 2-dimensional and 3-dimensional problems. So please take a note of it. In case of 1-dimensional problems, we already looked at this kind of thing. We plotted Jacobian, and then we have seen whether the Jacobian is always positive or not. But here we cannot plot. It's a 2-dimensional case. So we need to, here also we can do plotting. That plotting is going to be a little bit more involved. Okay. So that we will see. It's not simply checking whether J is above the datum line or not, because it's a matrix here. Okay, you please take a note of this. So okay, before we stop, anyway, we'll discuss about this valid mapping validity in the next few, or in the next example, which we'll be covering in the next class, tomorrow's class. Before that, you please make a note of this one. These two conditions. We'll see the implication of these two conditions in the next class. For a 3-node element, 3-node 1-dimensional element, what you learn, the mid-side node should not be close to the extreme nodes. Mid-side node should not be close to extreme nodes by quarter of the element length. Same logic is applied here. For 8 node element, the mid-side node should not be close to these extreme nodes by quarter of the, instead of element length, that particular edge length. So if the particular, here you can see this, whatever is caption that is given, placement of mid-side nodes for quadratic element. You please make a note of it. Suppose this is one of the side, what this is a part of quadratic element. That's why this is shown as a curved line. So this is one of the corner node. This is another corner node. This is mid node. So the length of this side is L. If the length of this side is L, this mid-side node, this middle node should lie between this point and this point. It should lie only if it is closer than here. Let's say this is here, then this is going to affect your mapping. Then your determinant of J, it's going to have some influence on the determinant of J that we just discussed. So the middle node should lie between this point and this point. Okay, that is one condition. And also the angle between the edges, should not be less than 15 degrees and should not be greater than 165 degrees for quadrilateral element. Please make a note of it. So if you violate these conditions, that is middle node, mid-side node closer to the corner nodes, or if the edges are too acute or too obtuse, then you will have problem with your determinant of J. So we will see what is the implication of these two things in tomorrow's class. Okay. So this is for quadratic elements, that is 8 node element, 9 node element, such kind of elements. And this is for all elements, all quadrilateral elements. Okay. So I'm going to stop here. Okay, thank you.